Thank you, organizer, for this kind invitation. And it's so nice to see so many young people attending Exoplanet conference. 25 years ago, I was the only person in the country to work on this field. Of course, I received tremendous help and advice from one of the outstanding collaborator who has been my collaborator for more than 2 decades, is Dr. Mark Marley. Currently, he is the director of the Lunar and Planetary Science at Arizona. Now, although brown dwarf and exoplanet was discovered on the same year 1995, but brown dwarf are not as popular as extrasolar planet because the ET or extraterrestrial life made it extraterrestrial planet a very hot subject. So the question is that what is brown dwarf? So first I have to tell you what is brown dwarf before I go to brown dwarf and then the exoplanet. The brown dwarfs are the link between the most massive, the heaviest planet and the lightest star. So they inhabit the realms between intermediate to heaviest planet and the lightest star. But these brown dwarfs are just formed like a star, but they have failed to become a star. Now, how a star is born? So we know that in our galaxy, there are various regions with huge interstellar cloud or nebula. They are made of mainly hydrogen and dust particle, like that you can see here. This is the Horsehead Nebula, and then there is Orion Nebula. These are originated by the mass loss or the supernova explosion of massive stars, and these are very cool of the gas, the extended light years distance, but they are the factories of star forming, the star formation. So we can see that the stars are being formed in this type of object, and basically these are very cool and very static gas. So they are so cool that their gravitational inward pull is balanced exactly by their thermal radiation. But if there is a perturbation by some supernova explosion or by some nearby collision, then this equilibrium condition, that is the hydrostatic equilibrium, is lost, and this huge clouds start collapsing. And it gets fragmented, and various individual regions start collapsing to give birth of new star. So if you see the individual star, what happened, as it collapses, its rotational speed, the spin rotation increases, and it becomes from spherical body to a disk, a pancake type of thing. A disk and matter start accreting into the core. So this method is called the core accretion process of star formation. Lot of matter get ejected in the jet formation, and the matter get accreted, the gas get accreted at the center. The center become dense and become very hot, and then the protostar is born. And after some time, the heat temperature becomes so high that the nuclear burning starts, and it becomes a star like our sun become. And therefore, this nuclear burning is a very important thing for determining a star. Now, usually in the normal star, like sun type of star, the nuclear reaction that takes place in the core is called the proton-proton chain. So if the mass of the core of this collapsing gas is more than 13 Jupiter mass, or about 1% of the solar mass, then the core temperature increases to about 3 million degree Kelvin. And under this temperature and tremendous pressure, 2 proton fuses to become a deuterium atom. So this is, and then some energy is released after that. Now immediately after this deuterium is born, one more proton fuses with the deuterium, and it gives rise to helium-3 atom. Now see, it happens that here, this chain reaction, this is called the deuterium burning. This can start only if the core mass is greater than 13 Jupiter mass. Of course, it depends on the metallicity of the star. This is for the solar type of star. And therefore, we know by definition that a planet cannot have at any stage nuclear burning, even the deuterium burning. So therefore, it is usually considered that this 13 Jupiter mass is the minimum mass of, maximum mass of a planet. Now, this hydrogen-3 atom, it is a isotope. This is a very unstable isotope. So it emits again another proton, and it becomes a deuterium. So the nuclear burning cannot sustain On the other hand, if the mass of the object is more than 80 Jupiter mass, or about 8% of the solar mass, then the core temperature rises to 10 million degree Kelvin, and at that temperature and pressure, two helium-3 isotope that fuses to become a stable helium-4 isotope or helium-4 atom, and then the nuclear burning sustains. So therefore, to become a star which can sustain the nuclear burning, you need minimum 80 Jupiter mass or 8% of the mass of the solar or solar mass. So this we can define as the minimum mass of a star. So now there is a gap between the maximum mass of a planet and a minimum mass of a star, and that type of object is considered to be a brown dwarf. This was theoretically predicted long ago in the early 60s by one Indian American called C.S. Kumar. So he predicted that such type of object may be possible, and because they will not sustain the nuclear burning, their radiation will come from the gravitation, from the release of the gravitational potential energy, and therefore this type of object will be a copious source of infrared radiation. And he named this object as black dwarf. But that time, black dwarf already used, the term black dwarf was already used for the end product of white dwarf. So therefore, astronomer Jill Tarter then changed the name into brown dwarf to indicate that this object is copious source of infrared radiation. But at that time in 60s, infrared astronomy was not developed. So we have to wait for another 30 years to discover the first brown dwarf, and the Gliese 229b, the first unimpeachable brown dwarf. It was discovered in 1995, led by again another Indian origin astronomer, Sri Kulkarni, led by Sri Kulkarni, by using the Palomar Observatory of Caltech, and this was immediately resolved. And this is the primary. This is Gliese 229a, and this is Gliese 229b. And why we consider this is a substellar object? How we know that this has not gone through helium burning? It has only initiated deuterium burning, because we found that the temperature, the effective temperature of this object is 809 degree Kelvin. No star can have temperature less than 1600 degree Kelvin. Then the estimated luminosity is about the order of 10 to the power minus 6 times the solar luminosity. And no star can have luminosity less than 10 to the power minus 4 solar luminosity. And then the estimated mass was 71.4, just below the limit of helium burning. But this was, at that time, this was a puzzle that this mass is found to be slightly higher as you consider the mass-luminous relationship with respect to the luminosity. But nevertheless, the confirmation that this is an unimpeachable brown dwarf or substellar mass object comes from the clear signature of methane in the spectrum, because this type of molecule cannot exist in the atmosphere of a normal star. So this spectrum, the methane spectrum, that confirmed that this is a substellar mass object. This could ignite deuterium, but this could not ignite helium in its core, and therefore it could not become a star. And this mass luminosity relationship is recently resolved by that 229b, Gliese 229b, in fact, is a binary brown dwarf. So one is 35, about 35 Jupiter, another is about 40 Jupiter mass. So this is resolved in that way. So now, after this first discovery of the planet, now you know there are several brown dwarf has been discovered, and our third nearest neighbor, the first nearest neighbor is Alpha Centauri, Proxima Centauri system. The second neighbor is Barnard star, and the third neighbor is called the Lumen 16AB, which is a pair of brown dwarf. And so our third neighbor is an object which was born like a star, but it fails to become a star. And the fourth one, this one is detected by WISE. This is called WISE 0855. This is actually a coolest stellar object this is so cool that you can put your hand into this stellar object. So this is about less than 200 degree Kelvin, the temperature. And so you can put your hand over that. So these two neighbors are now found to be brown dwarf. And once several brown dwarf was discovered and their spectrum was available, then it was clear. We have also from Himalayan Chandra telescope, we took the image of brown dwarf, one of the brown dwarf 2 mass W, and we discovered first that these objects are variable in the optical, which was indicating something that I will come into the talk. So that is telling the presence of cloud in their atmosphere. So this is this was already we knew that it was variable in infrared, but for the first time we detected optical variability also. So once that several brown dwarf was discovered and their spectrum, because you can see them directly, and their radiation is also not, although not from the nuclear source, but their gravitational potential energy, the release of gravitational potential energy gives they make them quite bright, and so we can take the spectrum of the nearby brown dwarf, and we can see that there is a systematic change in the composition, that there is a systematic decrease in the oxide and there is a systematic increase in the hydride. And more spectrum came, and then it forced us to add 3 more spectral classification in the stellar classification scheme. You know very well that O, B, F, like that. So with that, there were 3 more was added. Now with that, we have an overlapping with the exoplanet and the brown dwarf. Together, they are called substellar mass objects because they are below the mass needed to become a star. They are called substellar mass objects. Whereas this brown dwarf has ignited deuterium but failed to ignite helium, the planet exoplanet, whatever be its origin, it has failed to even ignite deuterium. So the temperature, the mass ranges from 0.11 solar mass to 0.076 mass, and that can be translated into 13 Jupiter mass to 80 Jupiter mass. On the other hand, the planet by definition less than 13 Jupiter mass, but we do not know so far what should be the minimum mass of a planet, because by definition we know that it has to be spherical by it should have sufficient mass to have a spherical by its self-gravity. It should clear its orbit, but you know that IIU definition is valid only for solar planets, not for outside solar planets. So that is because the IIU people were very clever, that if you apply the definition of the solar planets outside the solar system, then many of the brown dwarf will become qualified to become at least the binary brown dwarf will qualify to become a planet. But we do not know whether these objects are born like a star or they are born like a planet in a protoplanetary disk. So there is a limit also there, because we do not know how they are born, these huge planets, which are 6 to 8 times more than Jupiter, but are less than 13 Jupiter mass. They might be formed just like a brown dwarf was formed, but they have less mass so that even deuterium could not ignite, or they might have born like a planet, because we didn't see that how they were born. So they could be a sub-brown dwarf or exoplanet, we do not know. Here you can see that, and one interesting object, 2 mass 1207, actually this is the first direct image of a planetary mass object. So here the primary is a brown dwarf which has missed, which has failed to become a star because its mass is less than 80 Jupiter mass. And here this object, this is 6 to 8 Jupiter mass, which has failed to become a brown dwarf. Now we do not know how it was formed, whether it's a binary system like a star collapse by the core collapse or by a protoplanetary disk. So we may tell it according to it is a sub-brown dwarf or an exoplanet. Now the surface gravity varies from 300 to 3000 meter per second square. There is a degeneracy in the surface gravity of brown dwarf, whereas the surface gravity of planet has to be less than 100 meter per second square. Otherwise, if the surface gravity much higher, deuterium burning will start. So that's the limit. Now, depending on the spectrum, the brown dwarfs are divided into 3 classes. The hotter brown dwarfs are called L dwarf, whose effective temperature lies between 1300 degree Kelvin to 24 degree Kelvin. And there is a clear signature of primordial. So there are many L dwarfs, not all dwarfs are brown dwarfs. Some of the M dwarfs, they cool down and they become L dwarfs. But in those L dwarf where there is a clear signature of primordial lithium or lithium-7, then only we tell that this is a substellar mass object, because once the nuclear burning starts, this primordial lithium get destroyed. And so this is a litmus test. The lithium is a litmus test for the nature of the substellar mass object. Then come the T dwarf, which is slightly cooler, and the temperature ranges from 600 to 1200 degree Kelvin, and there is a clear signature of methane. Now all T dwarfs are brown dwarfs, because methane cannot exist in normal stars, or even if there is the temperature once upon a time was very high, methane could have not be there. So all T dwarfs are brown dwarf, and the faintest stellar object or substellar mass object, or the faintest object that is formed like a star, is called the Y dwarf. That was our wise thing. So this is 200 degree Kelvin to 600 degree Kelvin, and here we can see the presence of ammonia and methane. On the other hand, the temperature of a planet can go from 100 degree to 1200 K. So there are some planets discovered which are very young. So their temperature, the thermal temperature could be 1200 degree Kelvin. Or if you consider as a T equilibrium, some planets are so near to their star that their temperature is much higher. So there is an overlapping between the temperature of the stars and the brown dwarf. So as a consequence, and the size of these brown dwarfs are very similar to Jupiter's size. So as a result, what happened, since we can see brown dwarf, and some of the planets, the hot Jupiters, are very similar, the atmosphere of the hot Jupiters are very similar to the brown dwarf. Therefore, the properties of the brown dwarf's atmosphere can be extrapolated to the hot Jupiters. And if we know if you understand the composition, we know the chemistry and the physics of brown dwarf atmosphere, we can easily extrapolate it to the hot giant Jupiter that has been discovered. So that we'll see there. So that's why brown dwarf study was so important. And most of us, me and we all started our research with brown dwarf, and then we landed to a exoplanet in that way. So now we have to explain the observed spectrum. So to explain that thing, we have to model. So it's not that the model doesn't mean that it's a toy, I have made it, your model, my model, his model, like that model. It is basically a computer simulation which incorporate all the known physics, and then it mimics or it reproduces the observed spectrum. So, for reproducing the observed spectrum, we have to solve a couple of very difficult equations. So first of them is the radiative transfer equation, which is the integral partial differential equation that tells the story of the photon once it comes out after interacting with the atmosphere, with the medium. So this is the radiative transfer that tells the distribution of the photon. Now, coupled with that, we have to solve hydrostatic equilibrium equation, which tells the pressure, structure, and with respect to the altitude. And then comes the radiative equilibrium equation that gives the thermal structure of the atmosphere. And then comes the most important and very tedious thing, that is the statistical equilibrium equation or rate equation that tells her what is the composition and how the photon get absorbed, or it gets scattered, or it gets re-emitted. And then to close this whole equation, we have to solve also coupled charge and total particle conservation equation. Now, when these are all well known for modeling the atmosphere of stars. But when we come to this cool object like the brown dwarf or the hot extrasolar planet, the temperature is so cool that here the chemical equilibrium allows the formation of molecules, and that makes the life very complicated. So along with this, we have to solve the chemical equilibrium equation as usual. So now we solve all those equations, and for the statistical equilibrium equation or rate equation, that gives us the opacity data. So for that we take the most recent thing there, and we calculate the absorption and scattering coefficient. So this is based on the solar system abundances of Goddard and 2003. This is very famous. Most of the group in the world uses this Catherine Goddard's molecular abundances. And then the molecular database of Freeman et al. It is based on 2000. This is called Sonora. It is available online. But when I started it, nothing was available. So it was by collaboration this with the Arizona groups, this opacity was available. Along with that, we use sometimes is needed because this is some slightly incomplete. So we take the Tennyson et al., that is Jonathan Tennyson's exomole opacity data. That is also by collaboration, because it's very difficult that without collaboration somebody will give you open their bread and butter and you can freely eat it there. So this is by collaboration. And then the line list used to generate the molecular opacities is by Lukuji. This is a standard cases, and the equation of state is taken by Kempton et al. So here we have considered included apart from hydrogen and sodium and potassium atoms, we have included the opacity of 28 molecules. This is for both the brown dwarf and for the hot Jupiter. So depending on the equation of state, everything changes. What type of object we are now considering, but the opacity data remains the same thing there, and this is wavelength dependent, but it depends on the pressure, temperature, the absorption, and the scattering coefficient. So depending on that, we model the spectrum of T dwarf, T brown dwarf, that is the cooler brown dwarf. And we see from here, this is the theoretical model from 1200, 1000, 1200 to 600 Kelvin effective temperature, and the surface gravity is 1000 meter per second square. And when we match it with the observed data, so this is a fitting of the model with the theoretical model, we see that there are good fitting in the near optical, that is up to 1.5, but here the methane line has a mismatching. So because of this mismatching, we have to invoke the exomole, which has a better opacity data. But now I think the recent thing, Sonora has already updated their opacity data, and then they have adopted a better methane, but this was done quite a few years ago. So we see that this is very nicely, this fits, and actually we are concerned up to this 1.5, but still we update the model. So we see that for T dwarf model, it is much easier because it's it's less complicated. The temperature is quite less. But then the chemical equilibrium, the chemistry of the atmosphere says that these objects are the limiting objects where dust cloud or the cloud can form in their visible atmosphere. So how the dust forms there, then this cloudy or the clear sky, that changes the entire game. So here what happened, when the object is quite hot like M dwarf, then the gas that get evaporated completely and we don't get any cloud. So it's a clear sky for M dwarf or early M dwarf. Then for L dwarf, that is the relatively hot L dwarf, what happened, the cloud forms, the silicon get formed in the lower, and it get by the turbulence, it get in the upper atmosphere, and then it comes into the visible region. And then when the temperature drops, it precipitates or rain down, and then for the temperature for T dwarf, which is cooler, then the entire this cloud, the magnesium silicate cloud, that gets completely precipitated. So the T dwarf is cloudless, and so that's why we could match the T dwarf spectrum without invoking any cloud model, but we could not do it because of this. And then again, for the Jupiter type of thing, here we get the ammonia. If we further go there for planet, the Earth-like planets, water and all type of clouds will come. So cloud plays a very important role in the substellar mass object, in the atmosphere of substellar mass object. So we have to model, invent the cloud models if we want to reproduce the spectrum of L dwarf. So cloud models, which we consider 5 major condensates. This was taken by the collaboration Marley and Ackerman. So this is also standard model. So there is a balance between, in this model, there is a balance between the upward turbulent diffusion of condensates. Mainly this is the magnesium silicate or the silicate oxide, because here the silicon gets condensates into the visible region, and then vapor, and then downwards transport by sedimentation. So then it falls down and there is a equilibrium is maintained, because the surface gravity and the temperature is so appropriate here that the cloud remain in the visible region. But when the T dwarf, the temperature is less, so the cloud get rained down, it gets precipitated, and we get the clear sky. So this, and since this is a dust So scattering is also there. So we have to consider the dust scattering also. So mis-scattering, we can go to more complicated scattering mechanism, but we see that mis-scattering mechanism or formalism appropriately reproduce the spectrum. So with that, we model the spectrum. So this is from 2200 to 1400. So we model with log B 4.5 and the spectrum are L dwarf. But when we fit with the observed spectrum, we found that this black one is the observed spectrum. The dust is essential to make it to fit with the observed data. So the spectrum clearly tells that this L dwarf has cloud in their atmosphere, but that is a indirect evidences for the presence of cloud. So what will be the direct evidences for that? So for that, the prediction by me was that if there is a dust, the light from brown dwarf or L dwarf will be polarized. And on the same way, since there is no cloud predicted by the chemical equilibrium, so there will be no polarization from T dwarf. Now the problem is here that even the stars can also starlight can be also scattered by molecules and atoms. But then this is not resolved spatially. So we have to calculate the polarization. The detectable polarization is average over the disk. And most of the stars, the disk is perfectly spherical, which cancel out the net polarization, the disk average polarization. So here also it favors me, because these brown dwarfs are an object that they rotate very fast, just like Jupiter. Even they are faster than Jupiter. And therefore, this fast rotation, the spin rotation induces an oblateness, a departure from the sphericity. And that gives rise to a non-zero net cancellation of the polarization. So with that, I estimated how much polarization can be detected and how much and which wavelength. That is, if there is a magnetic field, the polarization will be in optical and other wavelength. But I predicted IJH band, so it is in the infrared and near optical band. And then I thought that nobody will bother me, because sitting in India, I am doing all this polarization thing, so who will bother it? So let me try to detect if really this prediction is correct, if there is really the brown dwarfs are polarized or not. So I borrowed Impol from Ayuka, which was at that time was in Mount Abu. So from Mount Abu to it was brought to Banyal telescope, that 2-meter Banyal telescope. On board it was put it, and we were trying to set up the instrument, thinking that nobody will do it. But then what happened, just within 1 year, a French group led by this guy, François Menard, who is, I think, who was the director of the Grenoble Observatory at that time. And he sent me a mail at that we detected polarization 98% by using the force 1 polarimeter on board VLT. That's it. And this is Professor Franz Allard, who was an expert on brown dwarf modeling and also in exoplanet. And so what happened, they observed 5 brown dwarf. Out of that, 4 brown dwarfs shown confirmed detection of polarization, and that makes a very high ratio. So once this polarization is detected, then of course many other people submitted proposal, and then this was become many other group also started detecting polarization, and subsequently many polarization was detected from many brown dwarfs. Now the thing is that I have to tell you what is this polarization, how this polarization origins, and how it is detected. Okay.
What is polarization? Technically speaking, polarization is the measure of the anisotropy of a radiation field. Light is a wave of electric and magnetic fields. These waves can be oriented in any direction. The direction of each wave's oscillation is called its polarization. Most light sources, including natural light, produce randomly oriented waves. We call that light unpolarized. However, if the light waves are in the same direction, we say they are polarized. A device called a polarizer lets us measure light polarization. A polarizer allows light of the matching orientation to pass. It blocks light of the opposite orientation. Unpolarized light will pass through the polarizer at any orientation. Now, how does light become polarized? Light becomes polarized either by the presence of a magnetic field or when light scatters off of a surface. A properly oriented polarizer can block this reflected light. Light can also become polarized from scattering off of gas and dust particles in an atmosphere. You can see this effect in the sky by rotating your head while wearing polarized sunglasses. The amount of light that gets polarized tells us about the gas and particle properties in the atmosphere. Polarization studies have helped us understand the atmosphere of the other planets in the solar system. The unpolarized star light becomes polarized when it scatters off high altitude haze or cloud in the atmosphere. However, if the atmosphere is uniform, the cloud is distributed homogeneously, or if the object is perfectly spherical, then the net polarization becomes zero as the polarization in all directions cancel out. But if the cloud is distributed inhomogeneously in band-like structure, or if the object is oblate because of its rotation on its own axis, like our Jupiter, Saturn or Earth, then the net polarization becomes non-zero. On the other hand, if a planet transits across a star or a satellite or exomoon transits a planet, then also the net polarization can be non-zero.
So incidentally, all the solar planets and their moons lights are reflected lights are polarized. In fact, the presence of sulfuric acid in Venus was detected through polarization. So that motivated that from brown dwarf to exoplanet polarization. So having this idea that actually polarization was detected, we have to model, we have to explain the observed polarization. So basically what we do, they divided into two parts, that we calculate the linear polarization at each local point on the surface by solving the vector radiative transfer equation, the formalism given in Chandrasekhar's book in 1960. So for the atmosphere, for usual atmosphere, normal unpolarized atmosphere, star or other thing, we solve the scalar radiative transfer equation that I showed you in previous slide. But here we have to invoke the vector radiative transfer equation, and we consider really linear polarization. Therefore, we have three Stokes parameter, I, Q, and V. But when we have a symmetry like a plane parallel symmetry or a spherical symmetry, then we have only I and Q. So two quantity will do the job. And for atoms and molecules, we incorporate Rayleigh scattering, and for dust scattering, Mie scattering. So this is the phase matrix we have to invoke for Rayleigh phase matrix and Mie phase matrix, which gives the distribution of the photon before and after the scattering, which tells the distribution of the photon before and after the scattering. So once we calculate the polarization at each point of the surface, then we integrate it, this polarization over the entire visible disk, because the net detectable or the visible polarization will be disk average when it is a point object, or disk integrated in the point object. So as I told you that if the object is perfectly spherical and the matter distribution, the cloud distribution is homogeneous or uniform, then the negative polarization will be cancelled out exactly by the positive polarization, and you will get no visible or no detectable amount of polarization. But we know that most of these objects in the solar planets, almost all the solar planets, the sun is only the perfectly spherical body in the solar system, and Saturn has the maximum oblateness. Earth has also an oblateness. So these are all rotation-induced oblateness. So brown dwarfs are rotating even much faster than the Jupiter. Jupiter rotates, 1 day, 10 hours per 10 hours. So like that, some brown dwarfs are so fast that their linear linear velocity, rotational velocity is 90 kilometers per second or like that. So if this oblateness, we integrate over the oblateness, there will be a net non-zero cancellation of the polarization, and that will give rise to the detectable or the visible amount of polarization. So this was then explained, the observed polarization was explained by separately by many paper on that. And once this polarization was explained and more predicted and precise model was found that what should be the actual amount of polarization and how it will go. So we have, in the initial stage, I consider only the single scattering polarization because I didn't have the full opacity data. But then once Mark joined in the group, so we got the opacity data, and then we include the full multiple scattering, and that gives a more realistic model of the polarization. That gives exactly how much amount of polarization and how they will depend on the oblateness, everything. And so many groups came forward to detect, and there is a large number of L-dwarf found to detect, found to be polarized. And till date, no T-dwarf has shown any polarization. So that tells that the T-dwarfs are cloudless, but the L-dwarfs are cloud and dust cloud of that. So this, there is a large number of polarization, but there's the only field parameter is the viewing angle, that this we cannot know the viewing angle with respect to the rotation axis, because the oblateness is perpendicular to the rotation axis. So this is a function of V sin I. So sin I is the viewing angle or the inclination angle with respect to the line of sight. And this is the J-band polarization. You can see the very high polarization. Some of the polarization was so high that it can only tell that there is a debris disk, and that is giving rise to the polarization. But so far, all this polarization was explained by a homogeneous distribution of cloud model and with the rotation-induced oblateness. Some excess, like which was showing 2% of polarization, it was found later on that they have debris disk or dust disk, which was giving the excess infrared excess, proves that they have debris disk. But all this brown dwarf the polarization can be explained by a homogeneous distribution of cloud, which was the initial model of the cloud, and with the rotation-induced oblateness. In fact, some of the observation tells that the brown dwarf which are faster rotator, they are showing more polarization. So the faster rotator are showing more polarization that favors the oblateness model, that favors the rotation-induced oblateness model. Until and unless another young group of people, by using planet imager on board Gemini, detected polarization of this, our third nearest neighbor, Lumen 16AB. Both of them are L-dwarf. So they have cloud. And when they send me their data, then I was puzzled, because Lumen A, one of the thing, the bigger one, is just relatively slow rotator, and so their oblateness is less. Even putting maximum amount of cloud also, I could not explain the polarization it gives. It gives much higher polarization. So we could not fit it. However, Lumen 16B, the polarization data could fit nicely with my homogeneous and rotation-induced oblate model. So this was by Maxwell, Miller, and et al. So this was the thing. So that gave us that means that our another assumption that the cloud is homogeneously distributed is not valid here. There may be additional asymmetry that is giving rise to the excess polarization. So that could be that the Jupiter type of band type of cloud structure must be there in Lumen 16A. And so we took a three-dimensional model and then we made a inhomogeneous cloud distribution. And once we did it, we could, this type of band model, we could explain the polarization, the slightly higher polarization of lumen A and B. So this was the case. So that led us and my student Aritro to make a detailed three-dimensional radiative transfer model, atmospheric model that can take both the inhomogeneity, the inhomogeneity in the surface. So this model, the oblateness model, was vertically inhomogeneous, but it was horizontally homogeneous. So now we made that both horizontally and vertically inhomogeneous. And so it took a three-dimensional model because now it has become azimuthal angle dependent. So this was the case. So then with that, we could model successfully of these things. And then there is another thing that at the same time, we predicted that if a brown dwarf has a planet, or if the brown dwarf or if a star, it is low mass star, very low mass M dwarf star, which has marginally dust particle that can be polarized, but that doesn't have any oblateness. But then the symmetry can be again broken if there is a planet crossed here. So this is called the transit polarization. So the transit polarization will give a time variable polarization. So you can see this could be a exomoon traveling through a giant Jupiter type of planet that has cloud. We'll come to that. These are the self-luminous planets which are very high or hot planet that if they have a moon, then this moon can break the symmetry when they transit it and they can give a polarization. Or if a L dwarf, if it has a planet, L dwarf, I have already shown you one L dwarf that had a planet. So L dwarf should have a planet also. If they transit, they can also give rise to polarization. And this is significant. This is comparable with respect to the oblateness also. So then, you know that this transit polarimetry, there is a system-wide, this was a very sensation. There was a system of planets, 7 planets was discovered from an object called TRAPPIST-1. So there are TRAPPIST A, B, C, D, E, F. In fact, the HCT, our Himalayan Chandra telescope, was involved in discovering the first planet of TRAPPIST-1. So TRAPPIST-1 is discovered by Liton. So here you see this is a M dwarf and this is an early M dwarf. So this temperature is at about 2200 degree Kelvin. At this temperature, there could be a thin haze in their atmosphere. Although this is a stellar mass object, but this is very cool. This is a M dwarf, and they should have. And the theory predicts that they, my calculation predicted that there could be a thin, along with Marley's cloud model, it tells that there could be a thin haze in the atmosphere, in the outer atmosphere of TRAPPIST-1. But the rotation period of this object is very small. TRAPPIST-1 is or spinning very slowly, so the oblateness will be very less. So there was a prediction that still TRAPPIST-1 should show polarization when its planet will transit it. That's the idea, that the symmetry will be broken when the planet will transit it. And then after a few years, a group indeed, this was transit polarization, which was predicted in 2018. A group indeed reported that they have detected polarization from TRAPPIST-1. Here, this was the, I think, this is a Spanish group. They use WHT, and I don't know which polarimeter they use. I didn't collaborate with it. So all the time, the confirmation was secret, and I was in a pleasant shock that first brown dwarf by François Ménard, then this also. So this was that. The transit polarization is, I think, more transit polarization should be needed, but it needs a bigger instrument, bigger telescope, because the polarization is very difficult to discover. Then we go to something by extrapolating. So which is if brown dwarf is the South stellar mass object is a huge surface gravity, then exoplanet could be its nephew or niece. So here we go for the planet now. So we extrapolate the brown dwarf to planet. So far, so this TRAPPIST model motivated actually, maybe incidentally. So here the argument is that some planetary atmosphere has condensate such as silicate or water. Like if they are hot, very hot, if they are very near to their star, or if they are very young, less than 100 million years, so they will be very hot, and the chemistry, the chemical equilibrium favors formation of silicon cloud. Or if they are cool, like Earth-like planets, there will be water cloud, or there will be ammonia cloud if or methane cloud like our Jupiter and Uranus. So here also similarly the chemical composition tells that there is a L type of planet. The temperature is near 1000 to 1500. Then see why it is less, because the surface gravity is less. So surface gravity is less than the cloud can survive in the optical region without precipitating. So the thermal energy, the upward turbulence will be balanced by the inwards, the lower, the downwards rain out or the sedimentation. So here also some type of L type of planets are there whose temperature may be very high, but then there will be T type of planets where that cloud will precipitate or rain down and it will be clear. Then again for Jupiter type of planet there will be ammonia cloud, and then if you go beyond that there will be Earth-like of planet, but those are not directly, I mean they are hidden by the starlight, unpolarized sunlight, but there will be water cloud. So now depending on this, we again the stellar radiation in the optical is usually unpolarized, and if they are polarized, you cannot resolve them because they are by the molecules, by the atoms only, and the Rayleigh scattering is very less, and that is in the blue region only, significant polarization by the molecular or atomic scattering, not in the far optical or near infrared. Then unpolarized starlight gets linearly polarized due to the scattering by cloud particles in the planetary atmosphere. The planetary disk is actually partially illuminated, giving rise to asymmetry. So here, unlike the brown dwarf, here the asymmetry comes from another way, and it's more asymmetry because we know that these reflected planets, they are now partially illuminated. So they are already giving a time-dependent or phase-dependent asymmetry, and therefore the disk integrated polarization will become will not cancel completely. And then, of course, the planetary disk is non-spherical, oblate due to spin around its own orbit, while introduction the additional symmetry. So therefore, two symmetry asymmetry will work, giving rise to high polarization. One is the oblateness, another is the partial illumination of their disk. So orbital, so therefore this reflected light, the orbital motion around the planet, the star yields into a systematic time variation in linear polarization. But the problem is here, the unpolarized starlight will mix up with the polarized radiation, and therefore if you cannot block, if you consider only the system, then the polarization will be very less, of the order of the ratio between the reflected light and the starlight, that is 10 to the power minus 4 to 10 to the power minus 6. And therefore, the polarization will be very difficult to detect. But if you can block the starlight somehow, then the polarization will be very high from the planet. So with that, we just thought that why don't we do such type of planet which can be directly imaged like that? Coronagraph, in the morning season, it was told about that how a coronagraph is used to block the star, and then the direct image is taken of the planet here. Now this is in the infrared, and these planets are found to be very massive. They are 6 to 8 and sometimes 10 Jupiter mass. They are young, they are younger than 100 million years, and therefore they are emitting thermal radiation, and therefore they are self-luminous. They are far away from their star, so they can be resolved from their starlight by putting a coronagraph, and they are very similar to the brown dwarf, L dwarf atmosphere. So they should have cloud on that. So you can see that there are. This is the HR 8799, where there are 4 planets are in the infrared, and these are this is the evolutionary model that tells that the mass of these objects are very high. The dynamical mass is still not possible properly to determine. But we do, so that's why we have a wide range of mass of this object. But nevertheless, they are very young, less than 100 million. So they are still emitting their gravitational potential energy through the radiation process, and they can be imaged by. So this is here even you can see beta pictoris B, even the protoplanetary disk is also visible here. And this is, I think, the inclination angle. The first time it is not necessarily all the time it is the face-on view, this directly imaged planet or self-luminous planet. Sometimes the inclination angle will be very high in that way. There is some more. There are several planets discovered by this direct imaging of self-luminous planet. And the atmosphere of this type of planets are very similar to L dwarfs. So we invoke our three-dimensional model to this model, and we predicted that polarization can be detected from this, and we calculated the thing. And this was predicted by Marley and me in 2011. And then another group, by using the same planet imager, which has a polarimetric mode on board Gemini South, has claimed to detect polarization from some of the directly imaged planet. And I was, this time, also I was one of the authors to interpret it, but this time we are ready with our three-dimensional model. So we have incorporated all type of things, the oblateness and the inhomogeneous distribution. So this was detected by Rebecca Chen, we call her Becky, and this was the rocks 42b, and this is beta pictorial B, the polarization is detected. There are a few more, I am not showing all this polarization, and this was explained by a paper, the three-dimensional model of this. So far, this is the observed, this is the directly detected or can be directly imaged object, whether it is brown dwarf or the self-luminous planet or TRAPPIST-1. So these are all directly imaged objects, and our prediction in most of the cases got matched with that, and it was relatively easier for detecting polarization from such type of directly imaged substellar mass object. Next job is to go to the reflected spectra, and those are the challenging things there. How to find out, how to probe the atmosphere of the reflecting planet. You see, not only it's not only because they are very close to their star, but the starlight also is a hindrance for getting polarization or even spectroscopy for that. So for our solar system star, like Earth, Venus, Jupiter, what we do that? We just can send the reflected light through the spectrograph, and we can take the spectrum, and we can tell that what are the composition of the atmosphere of this solar planet, because we can resolve them, and we are in between, we are inside the solar system. So in that way, even our space telescopes and our space mission, Voyager, Pioneer, all type of things, they took, even Pioneer had a polarimeter, they took polarization from Jupiter, and it found different type of polarization from the pole and from the equator. And then as I told that the sulfuric acid give high polarization in Venus, that was detected from Earth itself, and there was a polarimeter. But when we go to exoplanets, this is not possible, because now we are seeing a system, and then the planet is covered by the intense radiation of its star. So how to find out the spectrum of this planet? So that's called the transmission spectra of the planet. So there are clever methods that the astronomers follow it. So first, the starlight is passed to the instrument spectrograph when there is no transit, and they take the spectrum of the star when there is no transit. And next, they pass the starlight through the spectrograph when there is a transit. So now this starlight is passing, a part of the starlight is passing through the atmosphere of the planet. And so therefore this second spectrum is a mixture of the atmosphere of both the planet and the star. So the next job is to just subtract the first spectrum from the second spectrum, and you get the spectrum of the planet, and that is called the transmission spectra. That is the basic idea. Okay, now this transmission spectra is expressed in terms of depth. This is the transmission spectrum that is called the transmission depth. So this is the transmission depth is expressed as 1 minus flux of the star when there is a transit, when the transit is there, divided by flux of the star when there is no transit. And this you can express when, because this is the region blocked by the, this is the planet radius. So that means this portion of the starlight is blocked. And this is the radiation of the star that is passing through the atmosphere of the planet. So this can be, if you just write algebra, this can be reduced into RPA by R star. This is the radius of the star. This is the radius of the planet plus the atmosphere. So the RP is the radius of the opaque planet through which radiation starlight cannot pass. And RA is the radius of the atmosphere, total atmosphere here. So if you add it there, this is RPA. So this is the FPA. Now, how to calculate FP? Most of the model, they just calculate by considering that this is only absorbed. The starlight only get absorbed by the planetary atmosphere. And so therefore, if it is absorbed, it will reduce by exponentially e to the power minus tau by mu. Mu is the direction at which this radiation is going, and tau is the optical depth of the atmosphere along the radiation, that is the direction of the stellar radiation here. So usually we consider this direction perpendicular, but now this tau is calculated in this direction. But Jupiter type of planets are quite hot and they have thermal radiation also. And we know our Jupiter is also having some excess radiation. And this if they are young or whether if it is very hot, they have a thermal radiation. So if we incorporate the thermal radiation, we have to include one more extra term here. F thermal, this is the thermal radiation from the planet. This is the radius, so this is the, so this is the modified transmission depth equation if thermal radiation is taken. And this will be important in the infrared region because the thermal radiation come in the infrared. On the other hand, if you consider cloud in the atmosphere, you have to consider scattering. You cannot avoid scattering. So the scattering will be clouds, dust scattering and everything. And therefore, this simplified formula, that is the starlight that is passing through the atmosphere as a function of the starlight into e to the power minus tau mu will no more be applicable, and you have to solve the full radiative transfer equation with the direction here. This is the albedo, and this is the flux of the star, and this is the phase function, the Rayleigh scattering or the mean scattering phase function that tells you the distribution of the photon before and after scattering, and these are the specific intensity, and you have to solve it and then you find out. So we do the whole exercise. We make a huge computational computer code, and here we come with the collaboration with the University of UCL group to get the exomole opacity. And this is with my student Aditya Chakraborty, who is right now at AIMS, NASA, and this is Giovanna Tinetti, who is the principal investigator of Ariel project that will go very soon to the space to detect transmission spectra. So together we make a numerical simulation and we fit put the available data that was obtained by using Hubble and by Switzer, all those things, and you can see that this is nicely modeled with the cloud even incorporated, and the thermal is also showing important thing. So this was at that time 2021 WHT was JST was not launched, so we took a simulated spectrum in the infrared, and we see that at the longer wavelength where JWFST is there, the thermal radiation for hot planet will be very much important. So this is the spectrum through which the planetary atmosphere can be probed, where we have taken a details model. So here once again I remind you, model doesn't mean that your model, my model, his model, better model, good model. Model means that it is the reproduction of the observed spectrum by incorporating as many physics as possible. So therefore, if your physics are missing, you cannot match the observed spectrum. So it is the analysis of the observed spectrum, and thus to tell that how the physics and the chemistry is working on that object. So we have also calculated the transmission spectra of exo Earth, But as Subrat told, that it will be very difficult nowadays to find out the transmission spectra. JWST has claimed to obtain something like that, but around M dwarf star. This is a Earth, if it is put outside the solar system. So you can see the oxygen line and you can see the ozone line here in the longer wavelength. And you can see there will be weak methane line also. So now methane, in addition to oxygen 2 and ozone, methane also acts as a potential biosignature, but in a oxygenic atmosphere. So there are methane in Saturn, there are methane in Uranus, Neptune, Jupiter, everywhere, plenty of methane. Even there is a methane ocean. That doesn't mean that biosignature. But if there is an oxygen-rich atmosphere, then methane will react with the oxygen immediately and it will become carbon dioxide, and this equilibrium is maintained. This equilibrium is violated, it is broken if there is a bioactivity. So there will be additional methane will be produced, and before the methane is exhausted by the reacting with the ozone, there will be more methane produced by the life, by the living organism, that is by bacteria and other things. Therefore, methane in an oxygenic atmosphere acts as a biosignature. Only simply methane is not like that. But still, we are looking methane in Mars. We are looking if there is some activity underground or some oxygen level is there or not. So this will be the some tentative transmission spectra when our capacity, higher, bigger telescope, space telescope will go, and we can see the clear signature of ozone. And you know, this oxygen, this is at the initial stage of the Earth, there was no free oxygen available. All oxygen added up with carbon to form carbon dioxide, to add with hydrogen to form hydrogen oxide, silicate oxide, etc., until at 3.9 billion years ago, a bacteria called cyanobacteria started doing the photosynthesis, and from that photosynthesis, the oxygen molecule, and a little bit before that, there was a volcanic activity that formed the oxygen level, little bit oxygen molecule, but it is the photosynthesis by cyanobacteria and other plants that gives rise to this huge amount of oxygen, and that's why it is a biosignature. Now, this oxygen goes to the higher, the high altitude of the atmosphere, and then it gets dissociated by the solar ultraviolet ray and then form an oxygen atom. This one oxygen atom combines with one oxygen molecule and to form the ozone. So therefore, ozone is also a bioactivity and this is also a biosignature. So therefore, but in addition to that, we need to have the water signature. So those are different things. I'm not going to that because this is not the water signature should be there, but these are all theoretical prediction. I hope that one day we will find out all those things here. But here the situation is that some planetary atmosphere has condensate such as silicate and water. Stellar radiation is optically usually unpolarized. Unpolarized starlight gets linearly polarized due to scattering by cloud particle in the planetary atmosphere. And the planetary disk is partially illuminated, giving rise to asymmetry in the reflected radiation field. That's what I have already told it, that reflected light. And there's an additional thing. So with this, we have also modeled the hot Jupiter, the polarization. This is a three-dimensional picture. Now you see that one thing, that if you can detect the polarization, generally our detection methods are biased in the sense that we can detect only those planets whose inclination angle are very high. They are viewed only edge on, except the astrometry method or gravitational microlensing method or the direct imaging method. They do not need any inclination angle. In fact, gravitational microlensing doesn't tell what is the inclination angle of the star that way. But the transit method or the radial velocity method, they requires high inclination angle. That is, it has to be viewed edge on. But polarization, you can see that if the planet is orbiting even face on, there will be a constant polarization. There will be constant polarization. But if it is slightly inclined, then there will be phase-dependent polarization, and that will depend on the inclination angle. So this is the predicted value of the polarization. That will be the orbital phase dependent. So you can see that if the inclination angle, if it is face on, the inclination angle is 0 degree, then still there will be high polarization, but this will be time independent polarization. And if the inclination angle from 30 to 90 degree, there will be So this is a numerical problem, don't bother for that. So this is the phase. So here in this phase, it will be completely the daytime. So if it is not oblate spherically, it's perfectly spherical, then the polarization will be minimum. Here it will be 0 at this position, and then there will be this side, night side also. Here you will see 2 times 0. So 0 degree and to 360 degrees here, 180 degree here also again 0. Maximum polarization will be at this edge of that. So it depends on all those. So this was the theoretical prediction, and there was a claim long ago, but by some Swiss group, Bardiogina or something like that. Francisco, you may remember Bardiogina in Geneva Observatory. Geneva, no, in I think Zurich, she claimed to have obtained polarization from such type of object, but it was not confirmed by anything. So we think that one day, because polarimetry research is still in its infancy, it is very difficult thing to data, and we don't have many polarimeter also. We have right now, spectrometer itself is a very difficult thing. So we can do it for water cloud also. So theorists can do anything. This is my last student, Monica Singla. So she did estimated the polarization of an Earth-like planet. So this is the case. This is all about the thing. So we have, now we have a hierarchy. So from brown dwarf to exojupiter, which are very similar, but their surface gravity is different. So their distribution of matter is different. That's why the equation of take care. Then comes the mini Neptune and the super Earth, and finally the exo Earth, and then the exo moon. So far, no moon has been discovered outside the solar system. So that's a hectic effort is going on. Many people are suggesting many methods. So we also suggested photometric transit as well as moon, exo moon, at least around the directly imaged planet or the self-luminous planet can be detected through polarization. And the final goal of our civilization is to answer that eternal question: is anybody out there or we are alone? And that question will be answered only that day when the transmission spectra will show the biosignature. And so we started with photometry to detect planet. Then we go to spectroscopy to find out the composition of the planetary atmosphere. And next, maybe the polarimetry will be the potential tool to probe the atmosphere of all these objects, of this fascinating customer that bothers us so much. So from the omnipresent microwave background radiation to the pulsars, pulse to the planetary radiation, everything is polarization, as if let there be light and there was polarized light. And so in future, of course, I think nowadays also many people are working. I hope that many of you will take up this project, the polarimetry of substellar mass object and extrasolar planet. Thank you. So before I take the question, there is the advertisement. I have written 2 books on exoplanet. One is in Bengali, Groho Theke Grohantore Planet Sondhane. If you understand Bengali, then read this book, because this book has got the highest literature award by West Bengal government last year, Ravinder Puraskar. If you don't understand Bengali, then you have 2 options: either learn it or read this. Thank you. Exo world, exo Earth, yeah. The transmission spectra, yeah. So, nowadays, no instrument exists which can, even mighty JWST cannot do, but it depends on where these are transmission spectra, so it depends on the ratio of the flux that is coming. So from M dwarf, if the planet is around M dwarf, it is nearby, it may be possible for that, but there are some claim, I'm not sure, JWST is doing that same thing there. But right now, we don't have the technology to get even Earth-like planet around M dwarf star. So forget about solar type of star. So we have to go out beyond. See, it is only just how many years? 95 to 2025. It discovered only 1995 when I was just a PhD student at that time, and I was in India, sitting in India. I didn't know anything about all those things. Ground up when I went to USA for postdoctoral, and then only I realized that these two objects are discovered. Two very fascinating customers for us. Yeah, any more? Yeah. Age indicator, yeah, that's a very good question there. For the direct, for the brown dwarf and for the directly image exoplanet, there is a evolutionary models. I showed that France Allard, unfortunately she has passed away at a very young age. So they were, that group, the French group was expert on that evolutionary calculation. So there are evolutionary models, so that tells the age of this. So from that basis, I think this directly imaged planet and the brown dwarf's age are calculated. However, it is easy for brown dwarf case because we know the initial condition, but for the directly imaged planet, we do not know the initial condition. So when the dynamical mass was detected, there was a huge differences, the anomaly found between them. So that is not yet known, but it is certainly it has to be less than 100 million years. Otherwise, the luminosity age relationship will fail there. But we do not know exactly. For brown dwarf, we know from the evolution. Okay, the second question is I don't know because I don't calculate this opacity. There is a big industry which calculates this opacity data. By Goddard has included the chemistry. Before that, the Friedman group, the ExoMol group is there. They have a huge computer data things there. One by one, there are millions of lines they calculate for all type of molecules. So we take the opacity data. From that opacity data, by using the pressure and temperature, we calculate the scattering and the absorption cross section. So if you go to the any standard atmospheric model, you will see that from that opacity data, you have to calculate the absorption and scattering cross section, which depends on the surface gravity and on the pressure distribution. And that is used to calculate the optical depth. In fact, when we model the atmosphere, we actually take that optical depth. And what is this optical depth? It is the inverse of the path traveled by the photon before it gets completely lost. So it is the that how much distance the photon can travel before it is lost. So that is the optical depth. So this optical depth is invoked in the radiative transfer equation, the tau, and the tau come from scattering and absorption cross section because the total optical depth is determined from this scattering and absorption cross section, and this scattering and absorption cross section comes from the opacity data. This is your second question. The first question is magnetic field. Yes. Magnetic field is there. Jupiter and Saturn has very strong magnetic field. But here the problem is that if for exoplanet, there could be magnetic field, there could be polarization, of course, will not be in the JHK band or I band or even in the optical, it will be in different band. So if you are talking about the radio in that way, that will be polarized. But the problem is that this is a unresolved system. So if you get a radio signal or polarized signal, you cannot tell that where it is coming from, whether it is coming from the planet or a moon or the star itself, or there is some comet falling or something like that. So it's practically, theoretically, it is okay. You can assume that these are, if you extrapolate the solar system, then Jupiter, Saturn has high magnetic field. Their light is also polarized. Of course, the observed polarization was due to scattering only, the cloud scattering, but the polarization is there due to magnetic field also. But here you can resolve it. You know that that is Jupiter and the radiation coming is from there only. And that Europa and all those planetary radiation, that charged particle is rotating and giving rise to the radio wave. But for this exoplanet, which is a point object, you will not know what is the source. Only you can speculate. That is the problem. But for scattering polarization, you know very well that the starlight is unpolarized. Unless it is a early M dwarf, like TRAPPIST one, which has a hedge, but that is also a hedge. It is the asymmetry is, if you take individual polarization of TRAPPIST one without the planet transit, the polarization will be very less because it is rotating slowly and is perfect, almost spherical. But here what happened, the symmetry is broken by the transit of those planets. Okay, so Cloud is formed only in the substellar mass object there. And that includes both L dwarf, not even T dwarf. Y dwarf again will show polarization because ammonia cloud will be there. And then Jupiter type of hot Jupiter. And then there will be, of course, our Mars will show high polarization. Even, you know, Moon shows high polarization because of the reflected light. The Moon surface is not smooth. So high polarization moonlight, even it doesn't have any atmosphere, but the reflected light from the Moon is also highly polarized. And we know very well Venus is highly polarized. Yeah. You are not from the? You should sit with me after the dinner and I will teach you. Whatever, yeah. We have done already, Orithra has done, and we have done the 3D simulation. See, here what happened when we do the plane parallel symmetry or something like axial symmetry, we take only r and theta. But here we have to take r, theta, phi. So in that way, it is the 3-dimensional. Yeah, there are formalism for that, the grid. That's the tricks there. So we divide small region into small pixel, and then we add up with that. So there's a technical thing there. So for a separate subroutine works for that. Once we calculate the polarization at all the parts, so then we integrate this radiative transfer equation with respect to r theta and phi also. See, each we consider 16 azimuthal point. Each azimuthal point has 32 angular points, and then we normalize. So this is a Gaussian integration point. That's why 16 and 32 come. Yeah. Twenty 23. Yeah. Yeah. Those are the dominant molecule. There may be other molecule also, but whatever observed spectrum tells us about the dominant molecule or whatever we expect, we take that. But see here, what happened? The thing is, for brown dwarf, it is just an extrapolation of the laboratory data. We cannot produce that much temperature, 1600 to 1800 degree in the laboratory, and that much pressure. Surface gravity is very high, so that this laboratory data is extrapolated up to that. So that's what the problem is there. But this chemistry people, Jonathan Portney is not Jonathan Portney, Jonathan Tennyson. So he's a chemistry guy. So he does that exomole databases. So by collaboration, they supply all those opacity data. From that opacity data, we calculate the absorption cross section, and that gives the optical depth. So there may be many other molecules also, but their abundances are very less compared to this. In fact, 8 to 9 molecules are sufficient for that. But we include it. It takes computer time very high. That's the problem. Very good question. Yes, no, we have taken, that's very complicated, this chemical. There are many people are working on the non-equilibrium chemistry, but we have here all those things are chemical equilibrium, because otherwise it becomes very complicated life. No, in whole life I cannot do it alone sitting in India. So you imagine right from 2000, I returned from US to here, and then I started doing exoplanet. At that time, I have only no opacity data, so I used the single scattering model. Then Mark joined with me, opacity. Then after that, all this group and many other people also joined. That's more than enough that I can do from here in India. Yeah, not only that, ground dwarf also chemical equilibrium. That directly image planet also chemical, or in everywhere we have used chemical equilibrium. Yeah, of course. So everywhere, not only transmission, everywhere you need the pressure temperature profile. So that we use some this component code also gives that pressure temperature profile. But It is radiative convective. Yes. So this is why Mark has a code which solves the hydrostatic equilibrium equation and thermal equation. So it is radiative convective because these brown dwarfs are heavily convective. Yeah. No, it's not isothermal. It's not isothermal. The temperature varies from. See, the effective temperature is what? Effective temperature is that the temperature related to the black body radiation like that. But when you take the temperature profile, the below is 3000 degree to 200 degree, it goes there. So different temperature structure for all the cases there. No, those are very simple models. So that's why the thing is that you have to solve in such a way that the radiation produced should be balanced by the radiation loss in between. So, and all those things you have to do layer by layer. So basically we use the discrete space theory where we divide the entire atmosphere into several layers, and then we integrate over each layer from up to bottom, and then again we go add up from bottom to top like that. So this was this radiative transfer code was made by me during my PhD time. Then I applied it when I was a postdoc to this brown dwarf model. And then Mark came and he included the cloud model. After that, this exoplanet came, become more difficult thing for us. And then that is called no that पूरा बिंदु पर्वत को लेके चला विसल्यकरण के लिए. So collected from people wherever is available and wherever not available, collaborated, put their name and they will supply you. So that's the way for the young people to do it. Yeah. Any more? Yeah. Yeah. They should not show any spectral feature because cloud doesn't show anything and the spectral feature will be completely suppressed by, so there will be no feature. Silicate, the magnesium silicate, silicate oxide, there are 53, I think those type of silicate molecules are taken for brown dwarf and for the directly imaged planet. For Earth, it's only water has been taken. And for Jupiter type of planet, some little bit of ammonia, methane, all those things are there. But I didn't have the that model for doing it, so I didn't do it. They are optically thick, they are homogeneously distributed, they don't they only absorb, there is nothing homogeneously absorb everything there, so it becomes flattened there. But I will say you the story that this GLIS 229b, initially we failed to model the near optical spectrum. Then we put dust on that to make the flux less. But then the Japanese group, they found out that it's because of the collision burden red wing of alkaline material. So these hot planets and the brown dwarfs, they have alkali metal in their optical thing, sodium, potassium. That's why we have taken the sodium, potassium. So it is not only the dust, it is the sodium, potassium line also sometimes visible for that. So that feature is there. But cloud feature is, it is suppressed. The cloud is scattered. No, it is not absorbed. It's just scattering. It is getting absorbed, it's up, and then re-radiate. So there are many physics are there. So that makes it featureless. But this is called forsterite, greyelite, silicate oxide, like those type of several. So in our model, this forsterite is the dominant feature, which is magnesium, silicon oxide or something, MgSiO3 side. Yeah. Very good question. Yes, there can be circular polarization if there is a magnetic field there. But here we have considered the particle, the scatterer, as a spherical particle. So if they are not spherical, if they are elongated, then they could have given circular polarization. But in that case, you have to invoke a mechanism to align those particles. So here we have considered only spherical particle. very simple spherical particle. That's why it is a linearly polarized. And also, since there is a axial symmetry, either plane parallel or spherical, so your V term, so these two terms get cancel out, the V term last. So you know polarization is expressed in 4 Stokes parameter, I, Q, U and V. So if it is axial symmetry, if it is linear polarization, V is 0. If it is axis symmetry, U is 0, like that. So the polarization, why we didn't consider the circular polarization? Because we have considered a very simple dust particle, because this model has to fit with the spectrum also. So this cloud model, if we take something arbitrarily, that will not fit the spectrum. So the same cloud model we have used, same atmospheric model that fits the spectrum and then the polarization. But if there is magnetic field, there will be circular polarization. Very well. But it is beyond our it's complicated. But so far nobody has reported any circular polarization, detection of circular polarization from ground dwarf. Nobody has detected. If somebody detects, then of course we have to do, we'll be forced to do it. Thank you for asking. Any more hand, leg? हाँ, there. क्या इतना जल्दी टाइम हो गया? अभी तो 3 मिनट है. हाँ? हाँ. Faraday rotation needs very strong magnetic field. This could be there. So that could, Faraday rotation will be for, not even for Jupiter. So it needs very strong rotation. So here this will be, there are in the spectrum, you can see this is called Zeeman effect. This magnetic field can give Zeeman effect on that. This much strong. See, Earth magnetic field is very weak that way. Jupiter and Saturn has a very strong magnetic field. Uranus and Neptune also has. But you need some mechanism for that. So some particle has to orbit and something so that the radiation will come from that. So just magnetic field will not give it. The radiation has to be modulated by the magnetic field. So as I told you that if there is radio emission, circular, this magnetic field, it will be mostly from the radio wavelength or longer wavelength. But it will be very difficult to distinguish that where it is coming from, whether coming from the planet or from the planetary moon or from the star itself, or means if something falls over the stars or something, comet or something like that. We do not know. It's a very complicated thing there. So, yeah, there could be, because if you extrapolate the solar system, there will be magnetic field. See, the magnetic field in M dwarf is very high, about 1,000 times stronger than the sun magnetic field in M dwarf star. But brown dwarfs are very neutral. So their magnetic field is very weak. Some of the brown dwarfs showed X-ray emission, but those could be some different mechanism, but they are very neutral atmosphere. So like this planetary atmosphere is also mostly neutral, but there could be some dynamo effect which could produce the magnetic field. So we know in Jupiter, in Earth, these are the dynamo effect. In Jupiter, it is not the dynamo effect, it is the liquid metallic hydrogen, the rotation of metallic hydrogen that creates the current, and that gives a strong magnetic field. Whereas in Earth, we have a differential core that gives the thing. The same differential core is there in Venus, but Venus is rotating very slowly, almost not rotating, so there is no magnetic field. And Mars doesn't have any differential core, although it is rotating fast, it has no magnetic field. So whether a planet has a magnetic field or not, that depends on its internal structure. Any more? Thank you.